Okay, so where we ended the previous lecture was here. Okay, we were doing loop gain analysis. So for loop gain, you need not close the loop, you can open the loop. So this is VE, this is V naught, GM1, GM2. And we saw that we could express this loop gain L of S in terms of A naught over this, where P1 and P2 are the poles, and P1, I mean, if I neglect the negative part of the term, it becomes GDS1 by C1, and P2 becomes GDS2 by C2. And then we saw that this, when you close the loop, becomes unstable. Not unstable per se, but it doesn't behave well because the zeta becomes close to 0. So in order to ensure that your zeta is 1, that is the critically damped case, we had to ensure that P2 was 4 times A naught times P1. So this is to ensure zeta equal to 1. Note that, again, I mean, this is obvious, but note that this concept of zeta comes only when you close the loop, right? Open loop, we are not talking about open loop zeta. This is closed loop zeta. But loop gain is for open loop case, open loop structures. So when we sketch the Bode plot, this is what we get. This is magnitude of L. And if we sketch the angle, what should we get? Let's say this is P1, this is P2, and this is omega U GB. So what should we get? What should the angle look like? Let's say it starts from 0. It should end at -180, but before that we have two poles, right? It starts from 0, then at P1 it drops. What will this angle be? -pi/4. Then it goes to -90. Then it will drop further a bit more. Sorry, not here. So something like this. Here. At P2, it will go another pi/4, and then it will go to -pi. Okay, and this line, this magnitude line, the straight line where it cuts, it's called the UGB because this is my 0 dB line. In the Nyquist plot, if I plot this real L, imaginary L, and this is my -10 point, this should look like, what should it look like? What should it start from? Right? Okay. Yeah, something like this. Correct? So now, what is this angle called? There is a phase margin, right? So this is the phase margin. Why? What is the implication of that? Why is that at all as something of importance? Why? Correct. Yeah, you had a question? Okay. So essentially, this is a measure of how far you are from this -10 point. If you introduce more time delay or more phase, right? If you introduce more phase lag, So this angle, right? So this angle here, this theta, what is that theta in Bode plot? That theta is nothing but the angle that the loop gain sees at UGB, right? So this entire circle is unity gain circle. So wherever your Nyquist plot cuts that unit circle, in the Bode plot, that corresponds to the point where you are cutting the 0 dB line, and the angle at the Bode plot corresponds to that theta. Which means in this case, the angle at this point, this will be the theta. And that theta is essentially the excess phase lag that we get. And that phase lag is minus pi by 2 minus tan inverse P2 by, sorry, omega UGB by P2. And why is this critical? This is critical because if I give it more phase lag than theta by this extra magenta angle, then I will be cutting that -10 point and my system will become unstable. So that is why that extra margin that you have is called phase margin, because that much amount of phase you can sustain before your system becomes outright unstable. Okay, so in case of zeta equal to 1, what is my UGB? Yeah, for a stable system, P1 and P2 have to be far apart. Correct. Yes, right. So because if you have to be strict, you can say that I can add minus tan inverse omega UGB by P1, right? So this will go to minus pi by 2, right? Because omega UGB, is much greater than P2, tan inverse infinity, or need not be infinity, like tan inverse even 20 goes to, pretty close to minus pi by 2. Okay. Okay, so I was hoping that you guys are comfortable with this, right? So this one. So how do you get the angle of this? Fine, and then? Yeah, that's what I did. Oh. At a particular frequency, and the frequency is omega UGB, right? Okay, fine. So now for a critically damped system, for a critically damped case, we know that this is A0. P2 is what? 4 A0 P1. What is omega UGB? You set this L of S to 1, and you assume that UGB lies between P1 and P2, and then verify. Right? So if I assume that you have to, again, you have piecewise linear curve, right? So you have to assume that UGB lies somewhere, then go ahead and do the calculation, and then see whether the approximations are right or not, or initial assumptions are right or not. So if I assume the UGB lies in this stretch of curve, then what is the equation of that stretch, or what is the expression of L of S? This will be A0 by 1 plus S by P1, but S is more than P1, so it becomes, and we set this to 1. So your omega becomes A0 P1, omega UGB. So if that is the case, this becomes A0 P1, and P2 is at 4 A0 P1. So naturally, my assumption is correct. So UGB lies within P1 and P2, somewhere within P1 and P2. And if that is the case, what is that excess? What is the total angle that we are seeing at UGB? So that is angle of L at UGB. is minus pi by 2 minus tan inverse omega UGB by P2. That is whatever omega UGB is A naught P1 and P2 is 4 A naught P1. So tan inverse 1 by 4. So this happens to be about 14 degree, 14. This is approximately 14 degree. So essentially, your phase margin is 76 degree for zeta equal to 1. Okay. So for a second order system, your if you have a second order system and you want the output to settle peacefully without ringing, but the fastest response that can without ringing, that is critically damped case, you require a phase margin of 76 degree. Okay, and as as you will see, all engineering disciplines have some way of hacking, or rather figuring out, simplifying a higher order stuff with a lower order stuff. So what we generally do is we say that even if you have a higher order system, right, third order, fourth order, fifth order, there I cannot define zeta. Zeta is only for second order system. But it's not necessary that because you know second order systems, all systems need to be second order, right? So systems can be multi-order, right? Third, fourth, fifth doesn't matter. But how do I relate the performance of those order systems with the lower order systems? We'll say that we'll do it through the domain of phase margin. We'll find out the phase margin for any order system, and we'll say that if it's 76 degree, it will behave similar to a second order system of phase margin 76 degree. That strictly is not true, but that's something we get by, right? It works. So that's why phase margin is such a popular, one of the popular margins. Okay. Yes. But yeah, go ahead.
So why don't we use that range of?
Okay. So his question is why zeta equal to 1 is critical, right? So why? So when you expect this to be your final output, right? If this is your input, you expect the output to settle instantaneously, but that does seldom happens. It will never happen. So it will be either be slow. So either it will be slow, or if you want to make it very fast, it will go something like this, right? So this is over damped, which is zeta less than 1. Zeta greater than 1. And this is under damped for zeta less than 1. Now, what happens if you go from, let's say, zeta equal to 1.5 to 1, right? So let's say this is zeta equal to 1.5, let's say, zeta equal to 1.5. What happens if I increase, if I go from 1.5 to 1, what will it look like? It will come faster, but it will not overshoot. But if this is zeta, if this is zeta equal to 1, now if I go from 1 to, let's say, 0.9, it will start overshooting. Yeah, even with 1 by root 2, it overshoots. It goes. In frequency response, it doesn't. In time domain, it does. That's Butterworth approximation. The step response by Butterworth rings. So what you are talking about is maximally flat frequency response, I think. Yeah. Okay, fine. So what is the takeaway from this? The takeaway from this is if we have multi-order system, in order to make it behave like a critically damped system, at least for all pole systems, we say that if we can manage phase margin of 76 degree, we are good. Okay. And in order to achieve that, we have to ensure that I have a 20 dB per decade roll-off at UGB. You cannot have more poles below UGB. For all pole system, no zeros, all pole system. You can only afford one pole before the UGB, not more than that. All the other subsequent poles has to be above UGB, right? Fine. So in order to do that, in this particular circuit, we had to split the poles. How did we split the poles? We had to we saw that we couldn't reduce capacitance. So we had to increase capacitance in order to move one pole to a lower frequency. And moving a pole to lower frequency essentially means what? I am adding more capacitance, which means I am slowing the system down. Right? Does that make sense? I'm adding more capacitance. The capacitance needs more time to charge, which means I'm slowing the system down. Yes. Okay. What happens if there are more poles before omega UGB? So what will it look like if there are more poles before omega UGB? It would have looked like whatever was there before we had applied this pole splitting, right? So let's say I have P1 here and P2 here, and this was before pole splitting. It would have looked like this. So what do you think the phase margin here would have been? It will go bad because now you will have an extreme case is this, right? An extreme case is if omega UGB is much higher than P1 and P2, then tan inverse each of those terms becomes -90, -90, it goes to -180, right? It's unstable, or rather marginally stable. So even if you don't go there, their phase margin will tank simply because you have two negative terms to deal with, right? Okay, so now the discussion was that how do we split the poles? We split the poles by putting a capacitance. Putting a large capacitance at either, you can split the poles by putting a large capacitance either here or here, doesn't matter. So we split, in this case, we put the capacitance, large capacitance on C1. So we basically increase C1 by a certain factor. And that factor, how much we need to split it by depends on this. Then you can figure out how much capacitance you can put. And from there, you basically back calculate and do the math. Now, the question is there any other way of going about doing this? Because putting a large capacitance, capacitance is essentially, how do you get a capacitance? You put a large metal and put another metal underneath, and you hope that it's large enough to get whatever large means. Now, as it turns out, in an integrated circuit, you cannot put capacitances. If capacitances of 10 picofarad itself are considered quite large. Okay, so which means that if you do the calculation and you find that you need 100 picofarad to stabilize, that is out of question. So you cannot really put very large capacitances just to stabilize a two-stage amplifier. So then people thought about it and say, that okay, if this is not something that we can do, what else can we do? So then, as engineers, people always figure out a hack of doing things, and one of the hacks is this. So if you cannot make large capacitance, can I trick the system into thinking a small capacitance is behaving like a large capacitance? By adding? That effectively means they are putting the area, right? We're increasing area, right? I do not want to increase the area. The question is, can I make a 1 picofarad capacitance look like a 10 picofarad capacitance without increasing the area? You can do anything you want. So in order to push the poles only, I need that, right? I need a large capacitance because I have to split the poles. So how do I get a large capacitance? So let me give you if you have not seen it before, it's slightly difficult to imagine, but once I tell you, it becomes very apparent. So let's assume you have a voltage control voltage source, right? So everything starts with that assumption, then we find that it's not possible, then we keep on changing, right? So let's assume, again, we have a voltage control voltage source of gain -8. Okay. So what if I put a capacitance here like this? May I help you? So what is the impedance looking in here? So how do you figure out impedance? You do the same old. This is V test. This becomes minus V test, A times V test. What is the current that flows through the capacitance? V test 1 plus A times SC. Right? So this almost behaves like looking in through here, I have a capacitance of value 1 plus A times C. Right? So if you apply a V test here, the current will be 1 plus A times SC. Okay. So this is one of the ways you can trick the system into thinking that, okay, you have a large capacitance. Okay. But the problem is very apparent that voltage control voltage source, right, of gain of A. That's what we were after. Anyways. But what does now the question is, what does a voltage source mean? Voltage source means that even if I don't have this C, even if I don't have this C, if I put a voltage V, I should get minus A times V. And even if I apply this C, this should be minus A times V. That's what a voltage source means. Whatever I connect, it shouldn't change. So this ideally is not possible, but is it possible under some approximate circumstances? That's what we are again after, right? So as it turns out, it's possible. And one of the, I will show you the math, and then we'll see why it's possible. This argument. Okay, so the argument is what you cannot get an ideal voltage control voltage source. What is an approximate voltage control voltage source? An approximate voltage control voltage source is something where you have to see that even if you connect something at the output, it doesn't really change whatever you are getting at the output, right? So whatever you connect doesn't load. That's what it means, right? So one configuration that you are already familiar with is this. Let's say you have a GM and you have an R0. If you don't connect anything and you apply V, this will be minus GM times R0 V. Okay. Now, if I apply a capacitor, or let's not apply there. If I apply a capacitor here, there is a certain frequency range where the capacitor doesn't load. Right? So what is that frequency range? Yeah, so that is associated with the time constant of this network. The time constant of this network is 1 over R0 C. Below 1 over R0 C, this capacitor will not load, and it will behave like a voltage control. It will behave like almost, even if I add a capacitor or don't add a capacitor, doesn't really matter. So what if I put this capacitor here? Right? What if I put this capacitor here? Will it load or not? As it turns out, it doesn't load for a certain frequency range. Okay. So now, I will show you the math and I'll try to convince you. But for now, let's assume if that condition is valid. If that condition is valid, where can I use this contraption? So I have that contraption here, right? So let me sketch it instead of going back and forth. And put this contraption here. Let me call this CC. Okay. So now the question is, what does the loop gain expression look like? And this loop gain expression will be similar to one of the problems that I had given you, the common source amplifier with resistances, capacitances everywhere, right? So the expression will be exactly identical. If you have gone through it, fine. Otherwise, I'll just show you. I think I had provided solutions also, right? Okay. So let me go back to. By the way, there is a name for this structure. A very famous name, very popular name. This is called Miller capacitance. named after its inventor. So if you simply write out the similar things that I have sent in your in the answer sheet. So if you simply write out the equations, you get two equations. This is one equation, this is one, this is two. Basically, you have to solve for V naught over Vi. Matrix forms is simple. You just put it in the matrix form. I'll share this with you. You don't have to write. If you now you do the algebra and you end up with this big nasty equation. Okay, so this is where generally maths classes end, but this is where engineering starts. So obviously you cannot design anything looking at this equation. Nobody can. So then we put approximations that, see, we are not trying to find out the roots of this equation under all conditions. We are trying to find out the roots of the equations under the condition that my two-stage amplifier works properly. For that, the poles have to be far apart. That is a condition that I know needs to happen. So if I am looking for that condition, why don't I impose that condition directly while finding out the roots? So if that is the case, we know this quadratic has these beautiful expressions. So if P2 is much greater than P1, you can say P2 is minus B by A and P1 is minus C by B. And you get two terms. I mean, we get P1 and P2, which still are pretty big, but we'll see why it makes sense. So if you do the algebra and you basically look at this term, this is what you get. Okay. This negative term comes because it's a negative left-hand side pole. Now, let's look at the denominator. Let's look at the numerator first, right? In the numerator, what am I seeing? So let's try to figure out the poles associated with this node, V1. Okay. So the issue with putting this capacitance CC is, with respect to the previous structure, here the two sides of the structures are not decoupled anymore, right? This part is loading the previous part. So in the earlier structure where we didn't have this CC, we could have figured out the time constant individually associated with V1 and V2, and then easily figured out what is P1 and P2. But the problem here is these two are talking to each other, right? So is there an approximation that I can use to ensure that still I want that first order kind of expressions where time constant is associated with a pole, with a node, and then try to figure out if I can decouple them as two first order terms. Okay, so let's see if that is at all possible. So time constant is of the form of some conductance divided by some capacitance, right? So what is the immediate conductance that you see associated with V1? GDS1 goes in the numerator. Okay, what is the immediate capacitance that you see associated with GDS1? C1 comes here. Okay. Let's not talk about these two for the time being, but if you look at the denominator, which term do you think is dominant? Among all these terms in the denominator, which one you think is dominant? Note that GDSs are of the similar order and GM is more than GDS, much greater than GDS. No, right? The first term is GM2 over GDS2. First term will be dominant. Now, what is GM2 over GDS2? Gain of the second stage, right? So this, let me say that this is the gain of the second stage. So if I say this is minus A, this is A is GM2 by GDS2. So what is the capacitance looking in from that Miller approximations? 1 plus A times CC, right? So this actually has to be CC. Okay, I used it C everywhere, so let me use C. So this is what you get here. Okay, so you get GDS1 by C1 plus some term which is dominant, and you get some two other pesky terms, and that we expect will be there because ultimately these two systems are not perfectly decoupled. You will have some extra term which will not make sense, but ultimately all you have to ensure is that they are not playing spoil sport in the sense that they are not dominant. I mean, one of the byproducts of making approximations, you will get something which are completely unexplainable. But as long as the explainable terms are dominant, we are good. And the explainable terms are these. Okay. So your pole now, the first pole is now at, instead of GDS1 by C1, and you had to put a large capacitance on C1 in order to ensure that the poles goes to much lower frequency. You can put a small, relatively smaller capacitance and use Miller effect to ensure that the small capacitance C behaves like a large capacitance of times A, right? Where the A is the second stage gain. Okay. So this is a very neat trick, but even a more fascinating thing happens with P2. In the earlier case, right? In the earlier case where you couldn't do anything with P2, right? I could have as well said that in principle, what happens if I move P2 to higher frequency? That would have been a very good thing to do. But we couldn't do that. Why? Because we couldn't reduce the capacitance. Correct. Right? But see, in this case, what happens? Again, I mean, you do with minus C by B and all those things, and you get a weird term. And this is, after you do some massaging of the expression, this is what you end up with. Okay. Yeah. These two, I mean, these two don't have any physical meaning. I mean, simply because we are approximating, there will be some terms which will not have any physical meaning. But as long as they are smaller, we are okay. Okay. So now P2 becomes this. So again, we have to try to make sense whether this actually makes sense or not. So P2 is a pole associated with V2, this stage. Okay. So again, conductance over capacitance. Let's do the capacitance first. Because capacitance terms look simpler. So the capacitance is, what is the first capacitance you see associated with V2? C2, right? Appears here, fine. But there is this term also. From where do you think this term originates? C series is C1. Do you see anywhere where C is in series with C1? No, I mean, C1 by C plus C1 is equivalent to saying this, right? Do you see anywhere? Where? Okay. So that to some extent makes sense. Again, so now let's go to the numerator. Numerator is supposed to be the conductance part. Okay, so if you disregard GDS1, right? If you disregard GDS1 and you try to find out the impedance from the outside on that side, right? If you try to figure out the impedance from this side, you will have some current flowing through this, correct? And that current will be Z out by C1 by C plus C1. Okay. So if I put a V test here, so the current that will flow through this will be C1 by C plus C1 S times V test. Okay. But the more interesting thing that happens is this. What is this voltage? If I neglect GDS1, what will that voltage be? It's a voltage gap divider, right? Between C1 and C. So that voltage will be C by right? Is that okay? So this is nothing but, right, if I apply V test here, what is this voltage I'm looking for? So this will be what? C by C plus C1 times V test. Correct? So that appears here. And what is the current that now you are exciting the input of a GM. So that will draw some current in. What will that current be? GM2 times that. Correct? So this will be GM2 times C by C plus C1 times V test. So now that current, so what is, now if I have to find out the impedance, right? What am I seeing? I am seeing the dominant impedance term will be contributed by V test over this I. So what is the effective conductance that I am seeing? Because of this, this will be GM2 times C by C1. Correct? And that is what that you see here. Okay. And again, you have a pesky term here, which doesn't have too much of relevance. But again, looking at the numerator, which term do you think is the dominant one? Assume C and C1 of similar order again. The GM2 by C plus C1 becomes a dominant term, right? So your P2 now has effectively is a function of GM2. P2 is a function of GM2 now. P2 is earlier, before this compensation, P2 was a function of GDS. So now do you think P2 is staying where it was earlier, or P2 has moved to a higher frequency? P2 has moved to a higher frequency. That's all the better, right? Now I can split the poles both sides. I am pushing the pole P1 at a lower frequency and moving P2 to a higher frequency. Right? So this is a fascinating way of splitting the poles using Miller capacitances. Okay. Yeah. So let's do again approximation, right? So if I see let's assume that C is much greater than C1, right? Approximation. So what is the dominant term on the top? It will be GM2. And everything is of the order of GDS, I neglect. And in the, or let's say even, this is of the same order, C1. So this will be GM2 by 2, let's say. Okay. What is the denominator? It will be C2 plus C1 by C plus C1 equals C by 2. No, C2 is there in the denominator, right? We are not ignoring that. Okay. So while calculating V test by I test, we ignore C2 because that gives rise to a capacitive current, right? And the capacitance is in the denominator. Conductance over capacitance. So you will get a capacitance current, but that will come to when you are calculating pole, the S contributions will go to the denominator, right? And the real contributions will go to the numerator. Right, the conductance over capacitance. So that's why that C2 term, whatever will come, will go to the denominator. Right? Okay, fine. So this is what the new pole P2 is. Earlier, my P2 old was GDS over C2. Correct? So essentially, your P2 has gone up by almost like a factor of GM by GDS. Right? It has gone to the right. So you are not only able to push P1 to a lower frequency, but you are able to push P2 to a higher frequency, which was not possible earlier. Okay, so that is one of the reasons this Miller capacitance is one of the most popular way of compensating two-stage structures. By the way, I have not used that term till now. This is what you call an opamp. This stuff is essentially what you call an op-amp. Okay. Okay, so we'll stop here. Any questions? Yeah. We'll see. I mean, I obviously will not analyze that. I'll just flash it once and see why all of them make sense. This is a very basic structure. But you were right. Yes.
Because then will be getting higher frequency inputs and not
Yes. Okay, it depends what you want, right? If you want a very high speed op amp, then it's good. But if you are wanting to ensure that high frequency blockers or disturbances don't come in, then this is bad. So it depends what you want. That's why you have custom design, right? You don't have one size fits all, right? That's why we get paid.